All right, so now there's something known as a complementary event, and the complement of an event is the opposite of the event. What in the world does that mean? So for example, if A is the event of rolling a 6 on a 6-sided die, so what we did earlier, then the complement, notated as A with this superscript C, is the event of not rolling a 6. So in general, what you can do is, if you want to find something that's not going to happen, okay, it's going to be 1, because that's 100% of it happening, minus the probability of it happening. Okay, so for example, in example 6, if there is a 14% chance of being left-handed, what is the probability of being right-handed? In other words, not being left-handed. So probability of being right-handed is 1. So that's because that takes care of all the entire space, right? That's that 100%. But I'm going to take away the 14%. And so when I do 1 minus 0.14, I get 0.86. Generally in mathematics, if the problem gives it to you as a percent, you want to give the answer as percent. If it gave it to you as a decimal, you give the answer as a decimal. So I'm going to say 86% is the probability of being right-handed. So that's the technique. Sometimes it makes solving problems easier, so you don't have to list out every single thing happening and then just finding it where it doesn't happen. It's much easier to do 1 minus the chance of it happening. Okay, so some other things. Independent and dependent. This is really, really, really important. 2 events are independent if the occurrence of one event does not depend on the other event. I'll just get rid of that. So it will not affect it, okay? So here's an example. Dice rolls are independent, right? Since rolling a 6 on your first roll does not change the probability of getting 6 on the other one. Does that make sense? Like, same with flipping a coin. You flip the coin once, okay, that's that event. But when you flip it again, it does not matter what you got the first round. Now, 2 events are dependent. Whoops. If the occurrences of one event does depend on the other event. Okay, so this example is, say you're choosing names out of a hat. I don't know, to be a captain of a team, okay? And a co-captain. Well, if you choose the name once and then you don't put that name back in, it's going to affect who is chosen on the second round, right? Because, Stacy's not going to be picked on that second round. So in general, drawing with, this is really important, replacement is independent, while drawing without replacement is dependent. Okay, so if I were to choose those names out of a hat and I chose one name and then I put it back in, then it's not going to affect my second round. Does that make sense? Because all my possible outcomes or events are the same. But once I take an event away and it doesn't go back in, well, that changes the probability of the second time of getting my results. So knowing if two events are independent and dependent is super important since it will determine how we calculate the probability. So simply what I was just saying. So this is really, really important. And, okay, if two independent events, A and B, have individual probabilities, okay, they are independent, they're not going to affect each other, and I use the word and, key, you're going to multiply these two probabilities together. Okay, so they have to be independent, and I use that word and, so I want them to happen at the same time. Then you're going to use multiplication. So let's make sense of this. Let's go to the casino. So example 7. A slot machine has 3 wheels that spin independently of each other. So I gave us a little visual here. Each has 10 equally likely symbols. You either can get 4 bars, 3 number 7, or 2 cherries, or there's an option for a bell. Okay? If you play, what is the probability? So for A, I'm going to ask you that you get 3 7s in a row. Okay, so imagine that there's 3 7s right here. Well, so I'm going to write probability 7 7 7. Well, what are my total outcomes? 10. I thought that was my highlighter. Or, remember, I could add 4, 3 is 7, 9, and then we have one of these, so 10. So, 10, and I have 3 ways of getting a 7. Okay, to get the next probability, they're independent, so that's why I can use multiplication. Well, my next probability is, they're independent, so it's with replacement, so that will be another 3 out of 10. And my probability to get the third one will be 3 out of 10. So if I do multiplication, I do 3 times 3 times 3, I get 27. 10 times 10 times 10, I get 1,000. Or, it's whatever they ask for. I can write it as a decimal. And if you remember good old math from a long time ago, you would move that decimal 1, 2, 3. So this would be 0.027. Or you can rely on your calculator in this class, which is really nice. So I could do equals 27 divided by 1,000. And there we go. Okay, so let's now talk about, well, before I go into the next one, that's really unlikely, right? So if they're saying like you can win the jackpot if you get 3 7s, wow, that is a 2.7% chance of that happening. So think about that before you go all in. The probability you get no fruit symbols. Okay, so there's 2 options here. You actually count up the ways you can get no fruit symbols. So probability no fruit. Well, this is my only fruit, right? I either have a number, a bar, or a bell. So that would be 2 out of 10. Or what we can do, just so you can see the relationship between it, we could find the probability of no fruit by doing 1. Oh, forgive me, right? This should not be 2. We got to count up no fruit. I counted up fruit. So if we have 4, 4 and 3, that's 7. plus a bell, that's 8. So I wanted to show you finding no fruit, and that's where I got ahead of myself. It'd be 1 minus the probability of getting a fruit, which is the 2 out of the 10. Well, if I find a common denominator, we get the same thing. So, either you can count up the ways of not getting it or do that idea of the complement. And you can do that division or leave it as is, but if I do that, it'd be 0.8. So 80% of getting no fruit. So it's probably not going to be worth a lot. They know what they're doing. The probability you get 3 bells. Okay. So 3 bells. Okay, well, there's only one way to get a bell out of the 10 times getting it again times getting it again. Remember multiplication with fractions, it's 1 times 1 times 1, 1 over 1,000. Wow. So remember, I get to move that decimal 3 times, so that's 0.001, which brings you to 0.1%. No wonder that's the jackpot. Look how slim chances it is that you get it. Okay, now D. I want to get 1 bar, and there's that idea, and 2 cherries. So bar and 2 cherries. Well, what's the probability of getting a bar? 4 out of 10 times, I want 1 cherry, right? And then I want 2 out of 10, forgive me. And then I want another cherry. So I did the probability of a bar, which is 4 out of 10, times the chances you get a cherry, which is 2 out of 10, times getting another cherry is 2 out of 10. Again, it's because they're independent that those stay the same. If I go straight across, 4 times 2 is 8, times 2 is 16, over 1,000. And again, you can just rely on your calculator, or no, because I'm dividing by 3 zeros, I move that decimal 3 times. So again, this is really slim chances, 1.6%. All right, let's try one more. Okay, now we're going to talk about cards. If I do ask you about cards, like on an exam, I will give you a visual like this because I have realized in my teaching career, not everyone's familiar with cards. So here are all the cards in a 52 deck. So all decks have 52 cards. All right, and then these are known as suits. So this is a club, a spade, a heart, and a diamond. Okay, if you select one card and then you put it back in the deck, so that's the important thing, okay? That means with replacement. That's what I was meaning earlier. And then I'm going to reshuffle and I'm going to draw a card again, okay? What is the probability that both cards you draw are kings? Probability that they're both kings. Okay, how many kings do I have? I have 1, 2, 3, 4, and my possible outcomes are 52. So it's 4 out of 52 to draw that first one. Now, if I kept that card out of the deck, it would affect that second probability. But I put it back in and I shuffle, then I still have 4 out of 52 chances of getting it. And this, I will have to rely on my calculator. So I'm going to go ahead and do equals 4 divided by 52. Or maybe I just want to do, real quick, I'm just going to show you step by step in case I lose you. 4 times 4, which hopefully we're all okay with, we know is 16. And so that's 16 out of, and now I'm going to do 52 times 52, 2,704. So I can leave it like that, or I can say a decimal. So again, it depends on what the problem wants. So I'm going to do equals 16 divided by that 2,704. And I get 0.0059. So I just went out as far, usually it's 4 decimal places to get a full picture, but keep going. You know, I will say ideally, because this number goes on, right? And I really cut it off on my paper. I think it's really good habit to leave as a a fraction, because then you're getting the full picture, okay? Where this is rounded. All right, so this is known as an exact answer, where this is known as rounded. It's always nice to give exact, unless they specify otherwise. All right, so let's just do 2 more. If you select one card, and then you're going to select another card without returning it, okay, so this is known as without replacement. What is the probability that both cards you draw are kings? So this is known as dependent events, where A was independent. Again, the idea there is that the second probability is not affected by the first probability. That's known to be independent. Excuse me, I have to sneeze. Okay, and so, okay, probability of getting a king. We figured out it's 4 out of 52, right? Okay. I'm going to keep that card. I have no idea what that card is. But if it's a king, right, that means I only have 3 options to get a king. And there's only 51 cards left, because I did not return that card into the deck. Does that make sense? So I end up getting 12 out of, and I have to do my calculator. What is 51? Get rid of that. 51 or 52 times 51. 2,652. If I want to see that as a decimal, I'm going to do equals 12 divided by this cell. So that's going to be 0.0045. And once again, it's nicer to leave like this because it's exact. Hopefully this makes sense to you, that this probability would be lower than this probability, right? Because you're not putting the king back in the deck, so you're going to get less chances to get it. So maybe you want to try C on your own and pause the video and just come back to see if you got it right. Or just keep listening. If you select one card, then select the other card without returning it, what is the probability that neither card is a king? All right, so I don't want no kings. So there's two options here because of that word neither that is giving me a clue that maybe I want to do the complement idea. Okay, so let me just find the probability that you get just no king on your first try. So that would be 1 minus the probability of getting a king. So I'm sure we could all use a little refresher on fractions. I changed that 1 to be a 52 out of 52. Take away 4 out of 52. When you go ahead and you subtract fractions, you only subtract the numerator. So 52 minus 4 is 48 out of 52. So this is the probability that you get 1 no king from the deck. So let's just go back to the visual real quick. Say you don't want to use the complement. Well, you could have counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, so forth, blah, blah, blah. You just wouldn't count the kings. All right, and that would have also given you 48 out of 52. But I'm not done with the problem because the problem says probability 2 no kings, right? I don't just want 1. And we don't return it. So the probability that you don't get a king on your first round is 48 out of 52. But the probability of getting it on the second round, because you're holding that card and you didn't put it back in, would be 47 out of 51. So I'm going to go ahead and definitely use my calculator. And I'm going to do equals 48 times 47, which gives me 2,256. And then I'm going to do equals 52 times 51. 2,652. And sometimes I like us seeing it as a decimal because it really sinks in how great of a chance we have. So I'm going to do this divided by this cell. Wow, 85%, 0.85. And because I rounded, and I should be clear with that actually in the previous ones, use this rounding symbol. Which hopefully that makes sense to you because let's go back up to the visual. There are all these chances to not get a king. So we really have a really good chance of those two cards not being kings. And so hence around 85%. Okay, I'll see you in the last video.